Okay. Hey, everybody. Welcome to phase 2. Before we get started, I want to give you all a big overview of this phase and what to expect this week. So on our homeroom, as you can see, I've added a couple bullet points just to talk about what the next couple of weeks will bring. So this week and next week is going to be some intense probability and statistics. I will admit that you don't need to know everything that's on our curriculum in order to do data science, but a lot of the material is just, it helps you interpret what we're doing later. So 11 to 17, probability and stats concepts. There's a lot there, which is why I created this doc here, which I mentioned briefly on Friday, but I have this concept questions doc here. As long as by the end of the phase, you can answer all of these questions to some degree, and of course you'll have time to later study up for interviews. As long as you can answer these questions, that is good enough. We will be doing much more applied statistics. Very few data scientist positions will actually have you doing will have you do what a statistician does. So as long as you can answer these questions, you'll be okay. These questions actually come from my own interview experience, come from past students' interview experience. And I would say if they ask you all of these questions, that's considered a very tough interview. So just to let you all know the context of what we're doing here. Okay, also in our homeroom, Friday is off for Juneteenth. So we've moved our weekly pulse check to Thursday. Also tomorrow, I have put here a hangout hour with a gather around link. So tomorrow at 4 p.m. Eastern, you shouldn't be doing anything. And if you're not, come join us. I have some fun icebreaker questions. I think it's super, super important that you all get to know each other because you all will be your own network for data scientists. What I use to sell this is that so many of my former students and my own bootcamp classmates as well, so many of them have gotten jobs from other Flatiron grads. And this is where your network begins. And I cannot emphasize how important it is. And also just have people who are in the same field that you can talk to about the stuff that you're learning. Super, super important. So if you can, please come to that tomorrow. It will be fun, I promise. Okay. Any questions before we start our material for phase 2? All right, let's get started. So topic 11 is probability. 12 to 17 is statistics. I will tell you that in college, I did 2 semesters of probability and 2 semesters of statistics, and this covers 80% of that. So it's going to be very, very intense, but I will make a note of what is important and what isn't. So what we're going to talk about today, what is probability and why it's important for us. We're going to talk about sets, permutations, factorials, combinations, conditional probability, and the law of total probability. We'll get to all of these in a little bit. To start, why is probability important? What is probability first? Probability of something occurring is its proportion of all possible outcomes. More mathematically defined, it is the event space out of the sample space. For example, if you're flipping a coin, the sample space is every possible outcome. So heads or tails. Your event space is what you're trying to calculate. So if you want to find the probability of flipping heads, 1 possible outcome out of 2 possible outcomes. Rolling a 5 as an example. Your event space will be 5. Sample space will be 1, 2, 3, 4, 5, 6. So 1 outcome out of 6 outcomes. This is a very basic definition of probability. Why is this important? Probability is the basis of statistics, which is what we're going to get into much more over the next 2 weeks. And also for data science interviews. As I mentioned before, as long as you can get through those concept questions, you'll be okay. But a lot of data science models and a lot of data science things that you'll have to interpret do have underlying stats, even though you won't be using a lot of the definitions that we talk about in statistics directly. A lot of the concepts are derived from statistics. So that's why it's kind of important to know some things. Okay, so terminology, the first 2 I've mentioned before. Sample space is all possible outcomes. Event space is the subset of a sample space based on the probabilities we want to calculate. We'll come up with more examples as we move on. The law of relative frequency is kind of the basis of how probabilities are calculated and how you use to think about probability. So We'll get into this later, but within statistics, there are two main fields. If anyone has heard of frequentist statistics versus Bayesian statistics, Bayesian we'll get to later, but this is where the idea of frequentist stats comes from. So the law of relative frequency just says that the probability of an event is the ratio of positive trials to the total number of trials as we do an infinite number of trials. So what this means is we say that the probability of rolling a 5 is 1 out of 6. The frequentist way of thinking about that is I'm going to roll a dice an infinite number of times. And there's actually a lab that demonstrates this as well. Let's say you roll your dice 10 times. The idea is roughly 1 out of 6 of those times, you will roll a 5. Better example, let's say you roll your dice 12 times. It's expected that 2 out of 12 times you roll a 5 based on probability. And usually that's not the case. If you've ever played any sort of dice game, that's not usually the case because 12 is kind of a small number. It is highly variable. Their outcome can be highly variable with very few number of trials. But the idea is if you were to keep rolling a dice infinitely, the proportion that will roll a 5 is 1 out of 6. So that's the whole idea of frequentist statistics. Bayesian stats we'll actually talk about later in this presentation. Okay, so the first thing we want to talk about is some terminology with respect to set theory. I saw that Taylor, you posted an article in our Slack channel that kind of alludes to, I think I saw the intersect and complement. So we're going to talk about it in a little bit. The main things to remember are terminology terms, union, intersection, and complement. So let's just set up this example. Let's say our sample space is 1, 2, 3, 4, 5, 6. Now here we have two events. So prior to this, when we talked about rolling a 5, the event space was just 5. Let's just say that event A is rolling a 1, 2, or 3, and event B is rolling an even number, rolling 2, 4, 6. We can set this up as a Venn diagram. So anytime you see two overlapping circles in a box, it's a Venn diagram. Important things to note about Venn diagrams. The box that surrounds these circles is actually very important. It's actually very important to the definition of your sample space. So just to set this up, this left circle will be A, so we have 1, 2, 3. This right circle will be B, because we have 2, 4, 6. And because 5 is part of our sample space, 5 actually belongs within the box outside the circle. So that's something that's important to remember, especially if you're defining more high-level set theory questions, which you will see in your labs. Okay, so because 2 belongs in both of these, we put 2 in the intersection of the two circles. So union basically is saying, all right, what belongs in A and in B? So let me just grab my annotator here. So for union, which is this one on the left, we say A union B. And A union B is equal to 1, 2, 3, 4, and 6 because it contains elements in both A and B. Intersection is slightly different. The mathematical notation is an upside down U, A intersect B. And for A intersect B, what is the intersection? So what elements belong only in both A and B? The A intersect of B will be 2. Now this one is a little bit different. This one is complement. There are several different ways that you can say complement. So one way that you might see it is, for example, let's say we have A. The complement of A might be denoted with a tiny c on the top for complement, or a different notation, which you might see in some places, a little apostrophe. If you see that, both of those can mean complement. And so complement is just anything that isn't in A. So basically anything that isn't in A, this actually should also be shaded the outside, but the complement of A should include should include 4, 5, and 6, because it's anything that isn't in A. So this outside part that isn't in A should also be shaded in for this to make sense. Any questions about this? Cool. These are just terms that are good to know. If you're ever presented with a probability question, these are terms that will likely come up. I'm also going to send you all a recording of something that I did about a year ago, going through probability questions. So if you want to see me like walk through the process of 5 or 6 probability questions that come up in your labs, I'll send those out to you. All right, any questions before we move on? All right. Okay, this is just some more theory. A lot of it is kind of self-explanatory, but there are 3 probability axioms. Axioms are sort of like rules. So first there's a positivity axiom, which is that the probability of an event is always between 0 and 1. Can be included, 0 and 1 are included in this as well. So you can have probability of something being 0, you can have the probability of something being exactly 1. If the probability of something is 1, that's called a certain event. So a certain event is an event that's equivalent to the sample space. This doesn't come up too often, to be honest, but good to know. A certain event is just like, on a 6-sided die, what is the probability of rolling a number between 1 and 6? The probability is 1 because that's all your outcomes. Next, the additivity probability axiom, which is basically saying that the union of 2 exclusive events, the probability of the union of 2 exclusive events is equal to the probability of event 1 and event 2 only if the intersection of 1 and 2 is equal to 0. So just to use this to demonstrate, if we go back to our Venn diagrams here, the intersection being equal to 0 basically means that there's nothing in the overlap. So if I had a slightly different Venn diagram, which let's draw that over here, if I had a slightly different Venn diagram where the circles are completely separate, and in a different example, let's just say in this one, there's 1, 2, 3, and in this one, there's 4, 5, 6. As long as they don't intersect, the probability of them together is just the sum of the probability. To contrast that with our example here, we have the addition law of probability, which if you want to find the probability of A union B, and by the way, this is A union B, it is A plus B minus A intersect B. The whole thinking behind that, and that actually does scale up to if you have more events as well. The idea of thinking about that is, let's say we wanted to find the probability of A union B, which is here. Yes, we can look at it and say, all right, it's 5 out of 6 because out of 6 elements, 5 of them are in the shaded area. But another way of thinking about it, if you want to break it down mathematically, in A, the probability of it being A is 1/2 because we have 3 elements out of 6 elements. Now the probability of B is also 1/2 because it's 3 elements out of 6 elements, but they're just different elements. If we sum those together, this becomes 1, which we know is incorrect. And why it sums up to 1 is because we double counted this 2 in the middle. So that's why we have to minus the intersect, which has 1 out of 6 elements. So that's why we get 5 out of 6. That's the whole idea behind the addition law of probability. If anyone has heard of the inclusion-exclusion principle, which you don't have to have heard of that, but if you see that word around, that's actually what that's talking about. The fact that you're double counting anything that overlaps, which is why you have to exclude middle parts. Okay, questions about this? All right, there will be a couple lab questions where they have you apply these formulas, and if they have any questions, just let me know. Okay, so next we're gonna talk about 3 things: factorials, permutations, combinations. These are just different ways of counting. So we're going to take a look at a few scenarios in which we're going to use either factorials, permutations, or combinations. So let's start with factorials first. A factorial is denoted with an exclamation mark. And how you mathematically work out factorial is it is the product of all positive integers leading up to the number. So n factorial is the same as 1 times 2 times 3 times blah, 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 all the way to times n. If you had 4 factorial is 24. Yeah, it's 24 because it's 1 times 2 times 3 times 4, which gives you 24. So probability counting use case of factorial is if you ever wanted to figure out the number of ways to arrange a certain number of objects, the answer is actually the factorial. So more specifically, if we had this example of the letters A, B, C, how many different ways can you arrange A, B, and C? Because there are only 3 different elements, you just take 3 factorial, which is 6. And that works out because we have 6 different ways to arrange A, B, C. Small example, it's easy to see how that works out. If you have 4 elements, you'll actually see that there are 24 ways to arrange A, B, C, D, for example. So that's a factorial use case to just think of the number of ways to arrange n objects. Okay. Next, we get a little bit more complicated. We're going to talk about permutations. So permutations and combinations are very, very similar. There's a very, very minor difference between the two, which we'll talk about in a little bit. But the idea of permutation is it is the number of ways to arrange k out of n items. And this is a formula which I'll talk through in a little bit as well. But here's an example. So let's say there's a band that has a catalog of 8 songs, but they are playing at a concert and they have to play a set of only 3 songs. So how many different 3-song sets are there? So if you have song 1, 2, 3, 4, 5, 6, 7, 8, a 3-song set can be 1, 2, 3. A 3-song set can also be 6, 7, 8. It can be any permutation of those numbers. Here specifically, you see that a different order of the same songs counts as a different set. So if I play 1, 2, 3, that counts as one set. If I do 2, 1, 3, that actually counts as a different set. So based on this, how can we find the number of sets this band can have? We actually use permutations. So a number of ways to arrange k out of n items. And this is the formula n exclamation point divided by n minus k exclamation point factorial. And how that works out is in this example, we have n is 8 and k is 3. So in this case, we have 8 exclamation point divided by n minus k, which is 8 minus 3 exclamation point, which actually works out here to 336. Now, another way of thinking about this, instead, if you don't want to do this math, or a simpler way of thinking about the math, if we were to work this out and like write out the factorial, we have 1 times 2 times so on, so on, so on, 2 times 7 and times 8. And then we divide this by 5 factorial, which is 1 times 2 times 3 times 4 times 5, right? If anyone remembers fractions, we can actually simplify this by canceling out the 1s, canceling out the 2s. We can cancel out the 3s, 4s, and 5s. And so we're left with 6 times 7 times 8. That's just a trick that's good to remember. And that's how we get to this, which is also 336. So that's a quick way to think of factorials if it is easier for you to think of it that way. So remember that permutation is used when you want to think of the number of ways to arrange k out of n items. So not every item is being used. The difference between this and our last example is every item was being used. If we're thinking of the number of 8 set songs that we can do, it would be 8 factorial. Okay, any questions before we talk about the next one? Okay, so next we're going to talk about combinations. So combinations, very, very similar to permutations that I mentioned before. Number of ways to choose k out of n items. But here the order of your items doesn't matter. Different formula, and I'll talk about that in a little bit. But here's a different example. So same numbers. Here I have a collection of 8 seashells, and I want to randomly pick 3 to give away. How many combinations of 3 shells are there? So the very minor difference here is the order of my seashells doesn't matter in the same way the order of my songs that this band is playing matters. So that's the difference here. For combinations, the order doesn't matter. So typically you'll see because the order doesn't matter, the number ends up a little bit smaller. Because order doesn't matter, in this case, if I said that each similar 3-set song in a different order, if that counts as the same order, your number will be smaller. That was not an English sentence, but I hope you understand what I mean. The idea is in combinations, the number will be smaller. So therefore, we add something to our denominator. So here, let me get my pen real quick. Okay, so here the formula is slightly different. Instead of n factorial over n minus k factorial, which is what we had before, we further divide it by k factorial. This dividing by k factorial actually is exactly what accounts for the repeated permutations. So here, basically, you can see, even though we have the same numbers of 8 and 3, the combinations formula returns 56 instead of, what was it before, 336. So in this case, order doesn't matter. In permutations, order does matter. Now, quick side note, in your labs, they'll have you actually hard code these formulas, which can be very good practice. I think it's a good practice to write functions and to be able to translate things from math to code. But if that feels like a lot for you right now, there are built-in functions within NumPy or SciPy. So just in case y'all were curious, there are definitely built-in functions. You just have to look them up. Okay, any questions at this point? Okay, so we're moving very, very quickly. So if a lot of this is being like very overwhelming, that is normal. Okay, so the next thing we're going to talk about is conditional probability. Conditional probability is the probability of something occurring given that something has already happened. And this is very, very important for Bayesian statistics. So remember I was talking about there are two fields of statistics, and one of them was like, if you do something an infinite number of times. The other field is Bayesian statistics. And the whole idea of Bayesian statistics is you're coming up with your probability not by running experiments infinite number of times, rather by trying to use as much prior information as you can. An example of this is, let's say you are doing a dice roll and you want to find out the probability of rolling a 5. In a Bayesian sense, an example of thinking would be like, okay, probability of rolling a 5, but my last 5 dice rolls have given me 5s. And so if you're just thinking about it that way, technically not true, but the idea you can think of is that, okay, what are the chances that I'm going to get 5 a 6th time? Likely less. So Bayesian probability basically takes into account things that have happened before when coming up with this calculation of probability, which is super interesting. And a couple machine learning models that we're going to be talking about, not this phase, but next phase, are heavily based on this idea of Bayesian statistics. So we'll come back to this in more depth later on, but something that's just good to remember is there's a conditional probability formula. So the notation for conditional probability is the probability of A vertical line B. What that means is, what is the probability of A given B has occurred? And I'll talk about different ways that you can interpret this. But the formula for that first is the probability of A intersect B divided by the probability of B will basically give you the probability of A given B. A way that helped me a lot to think about this is, what proportion of B is also A? So you're saying that B has already happened, given B. So you know that B is definite. You just want to find out the probability of A given B. I like to think of it as what proportion of B is also A. This may help some of you, this might not, so no worries if it doesn't. But this actually works out to the same probability of, okay, within B, what proportion of that is A? And this actually works out because that's what the formula is. So that's just another way of thinking about conditional probability. We will come back to conditional probability in topic 17, which we're doing next Friday. And we'll get more into conditional probability because that's more relevant for that then. But questions about this at this point? All right, let's clear this. And the next slide is actually my last slide. So That is another thing that we're going to come back to in topic 17. So it's going to look kind of intimidating, but not to worry for now. This last thing that we're going to talk about is called the law of total probability. Basically, it's saying that the probability of B can be calculated if we know individual conditional probabilities. So in this very abstract example, we so happen to have B given A1, B given A2, and B given A3, and A1, A2, A3 sum up to 1. Basically, they're saying that there's this formula that you can use, which is over here. And it says that the probability of B is the sum of the individual conditional probabilities given that each A segment is disjoint and there is no part of B that isn't part of an A segment. Why this is important, and I will show you all in the concept questions an example where it is important. This diagram helps some people. It honestly didn't really help me too much, but some people understand it from here. This kind of question is where it comes in handy. And I will say, like, out of all these probability questions, this is the one that has come up the most. So let's take a look at this question over here, which I will go through exactly how to solve this when we get to topic 17 next Friday. But for now, just know that when you're presented with this kind of question, try and connect that with the law of total probability. The question we have here is, if the COVID test has a 10% false positive rate and a 5% false negative rate, given that you tested positive for COVID, what's the probability that you actually have the virus? And assume that 5% of the population has the virus as well. So this doesn't really seem like it, but this actually does use the law of total probability to solve, which we'll actually walk through the steps of solving this next week. But just know for now, if you want to work it out on your own, and if you're already kind of comfortable with probability, feel free to work this out. The answer should be 33%, not what you assume of false positive. Yeah. So a lot of people think that, okay, well, there's a 10% false positive rate. If I tested positive, well, then 90% of the time it's a true positive. So the answer should be 90%. Yeah, I have COVID. But the probability that you actually have the virus, given these parameters, is actually only 33%. And we'll talk about it next week, why the law of probability works out here. Just because I feel like it's not super relevant for the labs in this topic here. But yeah, this is actually all I had for today. I understand that this is a lot of material. I will tell you, in this slideshow alone, this was maybe like 3-4 weeks of like probability class in college. So do know that it is a lot. I will send out a video of me walking through a lot of the, not a lot, but like 5 or 6 of the probability questions that are in the labs. So if you just want to see how I like to think through some probability questions, feel free to check that out. I'll send it to the Slack channel. But at this point, are there any questions? We did a lot of math theory today. So questions.
Yeah, can you walk through, there was one of the questions, I was looking at it this morning, that it was like A union B or A intersect B, I don't remember which one, and then it was like the complement. Like, how would you do that?
Okay. Let's see. An example of that. Actually, let me pull up. Let me see. What did I call that slideshow? Okay, let me pull something up real quick since we have time. Here, I have a slide deck, which is the one that you'll see me walk through in that video that I send out. Just give me a sec to pull it up. That is actually a fairly common probability question as well, where we use the inclusion and exclusion principle. Okay, so I'm not sure if it's the exact question that you're talking about, but this is one of the questions that comes up in the labs, which is, yeah, let's just set up the problem first. Let me just do this. Okay. So the question says, at a supermarket, we're randomly selecting customers and making note of whether they have visas or Amexes. Some customers own both. So you can assume that probability of someone having a visa is 0.5, someone having an Amex is 0.4, and the probability of having both is 0.25. So knowing these numbers, what I like to do first is set up the Venn diagram. In the video, you'll see like my thought process of setting this up. But basically, they said that probability of A is 0.5, or let's just start with the middle is 0.25, because the probability of both A and B is 0.25. That's in the middle. And then with a little bit of subtraction, you'll figure out that just A is 0.25, just B is 0.15, and then the complement of all of it is 0.35. So within that question, there are 4 sub-questions of probability that someone has at least 1 credit card, which you can see here. It's just the sum of, these 2 bubbles here. That one doesn't have the complement in it. What's wrong with my keyboard? Okay. Probability that a customer doesn't own any of the credit cards, that's when you would use the complement. So here, even though here you can see that here, none of the mentioned cards here. A way of doing this is, let me pull this up real quick. If you want to see none of the mentioned cards, it means that you don't have 1 card, you don't have both cards. So another way of thinking about that is the complement of A union B. And anytime you see a complement, you just take 1 minus. So anytime you see a complement, and it gets more complicated when you have more sets within sets defined. And in this case, the complement of A union B is just 1 minus whatever this is, which in this case works out to 1 minus 0.65, which is 0.35. I realize that this is a fairly simple example. Do you happen to have the specific example, or do you know which lab it's from? I can actually pull it up.
It was from the first lab.
Okay.
It was something like that, but that is helpful.
Okay, awesome. If this is helpful, that's good. I do recommend checking out like my solving of probability questions video. I will say that honestly, it's not very often that they ask you probability questions during an interview. A lot of the interview questions will be around like your data science projects that you're doing, and more around like ideas of machine learning rather than probability questions, because this is like, we're doing derivatives of this stuff and we're doing applications of this stuff. So probability questions don't come up as often, but good to know just in case. I'll send out that video where I actually walk through this. And as you can see, let me just escape from this. And as you can see, I walk through a bunch of other questions as well. So hopefully that will be helpful. Also happy to walk through any probability question you have during a 101. I spent years on probability and statistics, so I'm very happy to put that knowledge to use these couple of weeks. But yeah, that's all I had to share for today. Does anyone have any other questions? Okay, don't forget, oh yeah, Taylor.
One more question. When you have the Venn diagram with the 2 circles and there's the overlapping point, how do you call it when, I'm just trying to make sure my vocabulary is correct, but if you want to know what is the probability of B, but it would be like the probability of B minus the probability of A union B, like you're only looking for the 0.15. Like, what do you call that?
You'll see in the video, I used the non-technical name of that crescent moon shape, which is incorrect.
Okay.
But there are actually several ways to define it. Like in one, you can actually say, what's the probability of B? Oh, there's another one that is actually not often used, but it's a backslash and it's B excluding A. So I think that,
okay.
I'm not sure if that comes across in our labs, but if you want to just specifically look at this, like for example, this 0.15, another way of notating that is, here, let me just do this over here, is actually B, oops, it's B excluding A. That's a formal mathematical notation for that.
And to calculate, I mean, this is obvious looking at that circle, but the definition of B excluding A is the probability of B less the probability of A intersect B, right?
That's right.
Yeah, okay.
Yeah.
That's it.
All good. Yeah, it does get a little abstract for what we need to know for data science, to be very honest with y'all. I just want to set the expectation, just so like, you know, if you feel like you can't solve like all of these probability questions, it's not the end of your career in data science. It really isn't. So yeah, I just want you all to be aware of that you don't have to fully understand everything that's coming towards you in the next couple of weeks, because it does get quite abstract. All right, any final questions before we close out for the day? Okay, well, in that case, have a good rest of your day, everybody. I will see you all tomorrow at the same time, and try and make yourselves free for that 4 p.m. Eastern hour. Okay, bye, everybody.